Okay, we're given net force and mass. Net force of 2,000 dynes, a mass of 300 grams. How do we calculate the acceleration? Well, Newton's second law says the net force, of course we're given a net force in the x and in the y direction, okay? So net force in any direction multiplied by the, or is equal to the mass multiplied by the acceleration in that direction, so that the acceleration is equal to the net force divided by the mass. And that needs to become very intuitive to you. You can't always be thinking, okay, Newton's second law says F equals ma, so now A equals, what's A equal again? Let's see, it's F net over m, okay. You don't have to think about that. You want to use it enough that it becomes intuitive, although if you have to fall back on that actually very simple formula, you certainly can. Okay, so you find the acceleration by dividing net force by mass. And that's the way you're going to see me do it most of the time. You simply have to know that, as well as you know that you multiply mass by acceleration to get the net force. I won't say have to, you should. Okay. Again, you get away with just knowing that acceleration is net force multiplied, mass, net force is mass multiplied by acceleration. Okay, so we divide the 2,000 dynes of net force in the x direction by 300 grams, and we get our acceleration 6.7 centimeters per second squared in the x direction. A dyne being a gram centimeter per second squared, which when divided by a gram gives us our centimeter per second squared. Now the force in the y direction was given to you in newtons and the mass in kilograms. Okay, so there's no reason we can't do that calculation. We probably want to reconcile these units. If we're somehow going to create the vector, we want a common system of units. Otherwise, the components won't be commensurate. They won't have the same unit of measurement, and that's going to cause us problems. In any case, we just go ahead with what we're given. Okay? Now, there's nothing wrong with doing a conversion beforehand. I'm just going to go with what we're given, 2.3 newtons over 0.3 kilograms, and we can see how that works out to 8 meters per second squared. Okay? So, what we see is there's a lot more acceleration in the vertical direction, the y direction, than the horizontal. And if the y direction happens to be the downward direction, this is an object that's descending with the y direction downward with an acceleration of 8 meters per second squared, then that's that's a little over 80% of the acceleration of gravity. So maybe we might suspect we have something falling under the influence of gravity with some air resistance or some other resisting force. Okay, well, now the question is, what's our vector acceleration? Well, we multiply the force the acceleration in the x direction by the I vector, y direction by the j vector, and we get this result. Okay? And then we could, I didn't take the time to do it, but we could express all this in terms of, actually I did. Okay, I expressed the 6.7 centimeters per second squared in meters per second squared. A centimeter being 0.01 meters, so clearly this comes out 0.067 meters per second squared. Our net force is our 2,000 dynes times I, plus the 2.4 newtons times J. And 2,000 dynes, you can work out, is equal to 0.02 newtons. So we have this net force.